Good morning, good afternoon. My name is Boominathan from Indian Institute of Technology, Madras. My co-authors, my former PhD student, Dr. Dania and Dr. Varghese, and another co-author, Dr. Anil Joseph from Joseph Limited Coaching. The topic of my presentation is vibration measurement during blast into controlled demolition of a 70-story building at Cochin, India. Ground-bound vibration caused due to the blast into building demolition activities, particularly in densely populated areas, raise serious concerns about the strength and stability of adjoining structures and infrastructures. Generally, it will result to a combination of three types of ground motions: blasting vibration, backlash vibration, and touchdown vibration, as reported by Wang and Lee and Wang. And this vibration monitoring during demolition is essential to assess the damage induced to the nearby structure. This building was, as per the Supreme Court India order, was the building located at Maraduk Municipality, Cochin, was demolished in 2019 for violating coastal regulation norms. So in the present paper, the results of vibration studies carried out during this demolition structure is presented. So this building or apartment was situated in an ecologically sensitive coastal area. It was located distance 10 meters from the waterfront, comprises of critical strategy assets like underground oil pipe, gas and pipelines in the impacted area. The soil filter consists of predominantly soft marine clay up to 16 meters with a SPTN value of 1 to 6, then followed by a mediums to flatheads start up to 36 meters, then very dense sand up to 50 meters. The structure is RCC frame structure with shear walls, constructed in 2014, 35 years before the demolition, with a height of 55 meters. It is founded on the cast-in-stone piles with a determination depth of 42 to 48 meters from the surface. Before the impact of the blasting, the peak wall and part of the shear wall and other elements, so that the dead weight, building weight will be reduced approximately 50%. However, the estimated weight was, after reducing 50%, about 22,500 tons. So 500 plus explosives were installed within the structural elements, charging hole. It is tightly covered with the steel wires and geosynthetic, so that it can prevent throw of the rubbles and debris during the impulsion. Reweakening of the structures, as we told earlier, cutting out a portion of the shear wall and other structural elements. Initially, the central and column force are destroyed, then adjoining columns are weakened so that the building would collapse due to gravitational force. Actually, the blasting is carried out with a controlled manner, such as that the time of 1/100 seconds between two successive blasts. You can show the video taken during. You can see a lot of debris. And vibration measurements was carried out in front of that is either side of the waterfront. The distance of from 50 to 200 meters from the building, actually, about 8 locations. So in this map, you can see that this is the river backwater body, and this is the building where the demolition was carried out. So we have, you can see the large number of houses, residential buildings are located on the other side of the backwater. Therefore, we have measured vibration either side, actually here about 4 or 5 locations. Similarly, here also remaining locations, actually. And basically, the acceleration we are measured using visually type accelerometers. It's a fixed from the concrete block embedded into the ground. And we have used advanced data acquisition system with attachments of PC software. We are able to measure, we are able to monitor as well as record the vibration as digital data. See that during demolition, actual vibration recording. Initially, it's a noise. Actually, you can see now close to the blasting. You can see how much the vibration levels have increased. Actually, so we are getting some 3 stages. Actually, 3 peaks are we are getting. Actually, it has 3 different frequency content. This is the typical time step acceleration recorded. You can see initially blasting relatively low acceleration. Then when buildings are falling, you can see a larger acceleration. Then finally we are getting lesser acceleration. This is about close to 8 meters per second square. The velocity peak, from that we can get the peak particle velocity. Here also you can see that this particular case we are getting a larger PTV that is about close to 140 millimeter per second. These are the peak particle velocity shown for different locations, particularly close to the building. This first location close to the building, we are getting very highest acceleration and as well as velocity. And that may be due to the fall of the breeze nearby the sensor. Otherwise, away from the site, we are getting very less amplitude of radiation. You can see the frequency content. It has both the low frequency content 2 to 10 as well as high frequency content. Also, we have represented the result in terms of Aron's acceleration, velocity, magnitude, duration. For that, we have taken the threshold acceleration in the 0.05 c. You can see that particularly bracketed duration, so we are getting relatively less duration only from 4.5 seconds to 10 seconds. Okay, it's relatively short duration only. And based on this measured velocity, PPV versus distance we have plotted. This potential relation developed using the plot, and it is standardized in the form of P equal to Ax minus estimator of minus C, where K and C the site constant, it is the distance from the impact. These are these FSD constants. And generally, most of the studies show that there is no risk of artificial damage normal building due to vibration less than 15 millimeter per second. However, the damage of the building depends on the various factors, including type, quality of construction, and stuff, vegetation surrounding area, structural resonance. This particular case, because of that accurate duration is low, short, and also frequency content, therefore potential is relatively may not be significant. Therefore, no major damage of the building are reported. So finally, we can conclude that in this particular case, the PTV varied from 10 millimeters down to 140 millimeters. The duration was 1.5, and it has both low frequency and high frequency content. Because of the bracket duration is very short and very high frequency, there is a damage potential that are significant. And particularly close to the building that closer measured value close to the building is very high, that may be due to that this fall in close to the sensor. The proposed administration using the available data may be used to establish the PPV at other location. And I acknowledge the thank Maradu Municipal for funding this study, as well as the geostructural private limited for the assistance provided during the vibration monitoring study at the site. Thank you.